Okay, so let's look at functions and this notion of functions as machines. Okay, so functions are like machines which take in an input value x, apply some sort of mathematical rule to x, and like multiply x by 3, and then output a result value y. Okay, so let's say we have a box, a magic box with a machine in it, and this machine is a function that multiplies anything that comes in by 3. So if I put in x is equal to 1 in here, then we multiply that 1 by 3 and we get an output of 3, like a y value. If I put minus 2 into the box and I multiply by 3, then I get an output of minus 2 times 3 minus 6. Okay, and if we just look at an example here, here is from question 4, page 382. Okay, and we have two boxes here, two rule boxes, one after the other in this bigger machine, if you like, and this function. So when we put in a value for x, we're going to add 2 to that value, and we're going to multiply all of that by 3. Okay, and we're going to get an output. So the rule looks like this: x that we put in, add 2 to it, and multiply all of that by 3. Okay, so if we put in 1, 1 plus 2 is 3, times 3 is 9. If we put in 2, 2 times 2 is 4, times 3 is 12. 4 times 3 is 12, and so on. So for each input, x will get an output y. Input, output, input, output, as a result of putting it through this function machine. Okay, and we can say that the rule is x plus 2 all multiplied by 3, or we can say that the y output value is we just put the 3 over here, it makes no difference, is equal to 3 times x plus 2, and if we're just to work that out, y, or the function, or the rule that produces the output, is equal to 3x plus 6, 3x plus 6. So if I put in x of 1, I have 3 times 1 plus 6, and that's equal to 9, which is what we have here. Okay, and just a bit of notation. This set of numbers that we input into the machine, that's known as the domain, and the way I remember that is I say domain ends in in and input begins with in. That's the input set, 1, 2, 3, 4, and 5. And the output set is known as the range, and they are 9, 12, 15, 18, and 21. And just to note that for us to call this machine or rule a function, the rule or function, for it to be a function, it must produce only one output value for each input. So whatever the input is, it can only produce one output value per input. So now let's just look at some function notation. So how do we recognize a function in maths when we see it? Okay, so let's take, for example, the rule 3x plus 6, because we won't be writing rule everywhere. Okay, we'll use some mathematical notation, and there's 3 ways to describe this function 3x plus 6. We say f of x equals 3x plus 6, or f colon x, or f of x maps onto 3x plus 6, or y equals 3x plus 6. So there's 3 different ways. They're interchangeable. You'll see them here, there, and everywhere in maths, and they're used at different times. But either way of writing the function is correct. Okay. So, for example, if the input is 3 and the output of this function is 3 times 3 is 9 plus 8 is 15, then we could simply say f of x, when x is 3, is equal to 15. We'll be meeting with this further notation in a while. Okay, but now let's look at mapping diagrams. Okay, so for example, a function is defined as f colon x maps to 3x minus 2. Okay, so the 3x minus 2 is the rule. The domain, i.e. the input values of f are 0, 1, 2, 3 and 4. Represent f, this function, on a mapping diagram and write out the couples generated. So we'll see what couples are in 2 seconds. So the first thing to do is to make a table and note your x and set out your input, your domain of input, the domain of input values, sorry, the set of input values. Write down your rule, and then for x is 0, 3 times 0 is 0 minus 2, that's equal to minus 2. So if x is 0, f of x, when x is 0, is equal to minus 2. When x is 1, through the rule, f of x is 1. X is 2, f of x is 4, 3, put 3 into the rule and you'll get 7, put 4 into the rule and you'll get 10. So the notion of couples then, this function has now generated what we call ordered pairs or couples. And the ordered pairs are simply the x and the f of x, or the y coordinate. If you recall, there's 3 ways to write the rule. Y equals 3x minus 2, f of x maps to 3x, and f of x equals 3x minus 2, or f colon x maps to 3x minus 2. But basically, the 0 and the minus 2 come together to form 0 comma minus 2, and that's a couple or an ordered pair. 1 comma 1, 2 comma 4, 3 comma 7 and 4 comma 10. So now let's look at a mapping diagram for that data. Okay, so from the table, the outputs or the range is minus 2 comma 1, 4, 7 and 10. Okay, and the couples that were generated are these couples here, and 4 and 10 at the end. So if we're to draw a mapping diagram, we draw the domain at this side, okay, 0, 1, 2, 3, 4, and that's x. X goes to 3x minus 2, and on this side we put our range values, okay. So that's minus 2, 1, 4, 7 and 10, and we simply map one x to its corresponding y, the domain value to its range value, okay. And just, we mentioned this briefly earlier, but we'll just mention it again. Only a function it's only a function in maths when each input maps onto one and only one output. So each of these goes only to 1 here, not to 2. Okay, that would be wrong. Okay, we can have this mapping, well, just basically this can only map onto 1. Okay, never onto more than 1. So how can we tell if a function is a function or not? Well, the way to do that is to look at in the list of ordered pairs, okay, make sure that the input value is not repeated, okay. So for example, if we have a set of ordered pairs 0, 0, 1, 1, 2, 4, 3, 9, there's no input value repeated there, they're all individual and different. Whereas here, if we have, just say for some other function, ordered pairs that include minus 2, 1, minus 1, 3, minus 2, 1, well, there's a minus 2 there and a minus 2 there. So this data hasn't been derived from a function. So this data is not typical of a function, whereas this is, because the domain's values do not repeat. Okay, I just want to mention the codomain. If we take two sets, A, 1, 2, 3 as our domain, and B, 1, 3, 5, 7, 9, 11, and if we have a function whose rule is 2x minus 1, that would map these guys onto these. It would produce these couples or ordered pairs, i.e. 1 for x means 2, 2 minus 1 gives 1. Okay? So if we're to draw the mapping diagram, we put our range, our domain here, our inputs, and our our set of B elements here in this end, and we see that we only map to three elements of this set, and we've some left over. Okay, the set B, which is all drawn here, is called the codomain, and it's the set of all possible outcomes that this could have landed on. Okay, it didn't land on these, but it landed on these three here. But the whole set B, that's known as the codomain, the set of possible outputs. Okay. Okay, let's look at the notation for functions in greater detail. Okay, if we have a function f of x is equal to 3x minus 2, then f of 3 when x is 3 is equal to 3 times 3 minus 2 is 7. F of 10, i.e. x equals 10, is 3 times 10 minus 2 is 28. F of minus 6 is equal to, when x is minus 6, is equal to 3 times minus 6, which is minus 18, minus 2 is minus 20. When f is k, some variable, then we just put k in for where we see x. So f of k, so in other words, x is equal to k. So we have 3 times x, but it's k is our value. 3 times k minus 2, that's 3k minus 2. Look at this example here from the book. The functions f and g are defined on R such that x maps onto x plus 5 and g of x maps onto x squared minus 1. So find f of 3. We'll simply put x is 3 there, we get 8. Find f of 2k. Well, we need to put 2k where we see x is 2k plus 5. And find f of k plus 1. Well, where we see x, we just put k plus 1. So x plus 5 is equal to, oh, bear with me a second, I'm sorry. Yeah, apologies, I've pulled the 2 down from here. I shouldn't have done that. So f of k plus 1 is just where we see x, k plus 1 plus 5. So that's k plus 1 plus 5. So that's equal to k plus 6. Sorry about that, I misread that and pulled the 2 down. Anyway, what about when x maps onto x squared minus 1? So g, for this function here, g colon x maps to. So g, when x is minus 3, is equal to minus 3 squared minus 1 is equal to 8. And g, when x is 3k, is 3k squared minus 1, and that's equal to 9k squared minus 1. And when g, the input, the x value is equal to k plus 1, then we simply put k plus 1 in where we would normally have x as k plus 1 squared minus 1. So we break that open to be k plus 1 times k plus 1 minus 1, and that would give you that quadratic minus 1. They'll cancel, and that gives you k squared plus 2k. For example here, a function is defined by f of x maps to 4x minus 5. Find f of 3. Well, f of 3 is just pop your 3 in there. 4 3's minus 5 is 7. Okay, then it gets a little bit more complicated. Find the value for k, for which k times f of 3, which is 7, equals f of 10, whatever that is. Let's find what f of 10 is equal to by letting our x value in the rule equal to 10. So 4 times 10 minus 5 is 35. And so therefore k times f of 3 is k times 7 is equal to f of 10, which is equal to 35. So k must be equal to 5. Let's look at example 3, question 16, page 390. G of x, the function, is equal to 1 minus 4x. Find g of k plus 1. So our x value is equal to k plus 1. So if g of x equals 1 minus 4x, g of k plus 1 is equal to 1 minus 4 times that x value, which is k plus 1. So 1 minus 4k minus 4, okay, is equal to minus 3 minus 4k. So then they're saying solve the equation g of k plus 1, which is equal to this value here, equal to g of minus 3. So we need to find what is g of minus 3 by popping minus 3 in for where we see x in the function. So we get g of minus 3 is 13. So to solve the equation then, we simply say, well, g of k plus 1 equals g of minus 3. That's what they've asked us to solve. We plug in the values that we found for each of those, and we bring over our minus 3 comes plus 3, and we get minus 4k equals 16, so k must be equal to minus 4.